morning. These are going to be your new students in class, and we're going to do it by alpha. And the first group that we're going to call down is A through E. Alpha A through E. That's going to be students in class, teachers that need an ID. Please send them to the library at this time. We'll come back on and do the rest of your groups after we get this first one done. Thank you.
All right, so yeah, let's just review a few things, and then we're going to go into some probability stuff, go from there. All right, so when it asks you to like describe a distribution or like a graph, or it asks you to make a graph and then do it, always go over like your socks. Or if it asks you to compare like two different things, so compare them using these things. So the shape of it is, you have like different options here. So you've got, let's see, like, oops, I don't know, geez, symmetric. I'm like, I'm so off. That's not how you spell symmetric, is it? How do you spell? Whatever. Okay, so you got symmetric, which could be like this. I mean, there could be many different things as symmetric, whatever. And so you could have symmetric things. You could have skew to the right or the left. So to the right means like there's like a mountain, and you could ski down to the right. It tails off to the right. Skew to the left would be like the tail is to the left there. Another one, so maybe I'll just write a bunch and then erase them. So like uniform would be if like it was like similar throughout. Which sometimes if you only have like when we collect data in class and we're 10 to 12 people, sometimes our data looks like this, but it's kind of misleading because we don't really have a lot of data points. But if it's like really obvious, if it's like the same, there's like even distribution throughout, it'd be uniform. So like this could be like the probability of rolling a dice, and this could be like rolling a 1, a 2, a 3, a 4, a 5, and a 6. And so they all have the same probabilities. So maybe the outcomes were very uniform in distribution. Like I had 2 1s, 2 2s, 2 3s, whatever. Let's see, another one. So we talked about was normal distribution. So normal is like a really nice symmetric, they call it a bell curve. Jeez, did not do good. All right, and it centers around like the mean, the average. So that was one. Yeah, I think that's good. So shape, what's going on? Or like if there's clusters, like, oh, there's a group here and then there's a big group here. Like just describe what this thing looks like. So that's shape. Wow, nice. I'm doing really nice things. So outlier. Outlier is a data point that's far away, and to prove it mathematically is actually using a box plot. So maybe I'll go over a box plot real quick, maybe draw one randomly here. So you've got your smallest value, your Q1, your median, your Q3, and your maximum. So the Q1 is the median of the first half. So the first half of your data, the Q1 is the median of it. Median is just line them all up in a row, smallest to largest, and where's the exact middle, or like count off until you get that middle value. So Q1, Q3, and so if I have an outlier, it's actually going to be, maybe I think that this lowest value is an outlier, it would actually be like a dot on there, and then there would be like a line. So to prove if it's an outlier, what you do is you take the interquartile range, which is the IQR. It's just like, where's the middle 50% of our data? So like, how big is our range in the middle 50% of this chunk of data? And then we're an outlier if I take this IQR and I multiply it by 1.5. Almost. Jeez. Alright, 1.5 times the IQR. And then, so if I take that from the Q1 and I go 1.5 IQR less than, I go from the Q3 and I give myself a range of that same thing. So if I'm below that or above it, then I'm considered an outlier. So like, let's say that this was like an interquartile range of 8. So 8, let's see. So if I was doing an IQR, 1.5 times 8 is 12, I think, hopefully. And then what I do is 12 is like my most I can go away from these two values. So I go from the Q1 and I minus 12. I go from the Q3 and I plus 12. And so I got to make up some more numbers here. So let's say I say that this one is 30 and this one has to be 38 then. So 30 minus 12, I'm giving myself a lot of math to do, is 18. 38 plus 12 is 50. So if I am outside of 18 and 50, then I'm an outlier. If nothing's outside of that, then it's fine. So like, since I put a dot there, let's say that that was the number 17 or something. It's an outlier. So again, I'm kind of just thinking off the top of my head, random review stuff. I didn't intend to go into all the box plot stuff, but that's okay. So IQR, we use it to get like an outlier, just a way to prove mathematically, oh, this is definitely too far away from my data. Alright, I'm not going to worry about it too much. Let's see if this works. Hey, it did. Okay, center. So center of your data, the way typically do that is you've got mean and median, and then for your spread, you can talk about standard deviation, or you've got range IQR. And we typically group these things together and we choose them. So I group these, group those. We choose them based upon the shape. So maybe I'll just continue this up here. So like, if the shape is symmetric, there I go. Oh my goodness. All right, whatever. Asterisk there. So symmetric, then you've got like skew or uniform. Well, I guess uniform would be symmetric, like skew, or like maybe it's just in clusters, whatever. Skew or non-symmetric, basically. Let's see. But then is there an E there? Is that better? Oh, I can't finish that. Whatever. I don't know how to spell symmetric, I guess, off the top of my head. Okay, so if it's symmetric, the center of it is the mean. That's a good, because like, let's just take this one. The mean and the median are like both right there. And typically the mean is a pretty good value to find, like the average is pretty easy. But if it's skewed, so let's just go like skewed right. Here is like the median, and then here would be the mean. So the median is a better representation of the middle. for like a skewed or non-symmetric data. It more accurately gives a description of where we're at. The mean gets pulled to like these high numbers over here. Alright, same thing. So like standard deviation is a value that talks about how far I typically am from the mean. So if the mean is a good number, standard deviation is a good number because it talks about how far most typical values, average values are from the mean. Range and IQR would be on this one, just like they would give me a better idea. IQR is like the middle 50%. Jeez. So IQR is like the middle 50%, which might give a description of like a bunch of my data is like right here, squished together, and not over here. So like choosing which one's where. And so when you like go through shape, outlier, center, spread, it gives you like a full description. You've really kind of talked about everything you need on a graph or whatever. So yeah, I'm just not going to go into it too much. I'll just kind of hit on it and go. Okay. Let's see, my other note, I had us talking about normal distributions. And so this is like our data. So I have a dot plot or whatever, and it has a lot of values here in the middle, not as many on the ends. And so, I'm trying to think of all the different things. Let's just say, I don't know, let's go for like, isn't like 100 like an average IQ? Let's talk about IQ or something. Because I think IQ does follow, like an IQ test follows a pretty normal distribution. Let's say you have like an average IQ of 100.
Teachers, pardon the interruption. If you have students that are in your class that are new students with last name F through J, please send them to the library to get their ID at this time. Again, if you have students who are new to your class that do not have an ID, last names F through J, please send them to the library at this time. Thank you.
Alright, so you have a mean, you have a standard deviation of 10. So mean and standard deviation of 10. So let's talk about one thing. Let's talk about like let's talk about a z-score, a standardized score. So put into perspective of like a z-score is how many standard deviations I am above or below the mean. So let's say that I took it fresh off a holiday break and I scored an 82 because like I don't know anything right now, I guess. So z-score of 80, or I'm a score of 82. So what is my z-score? Like how many standard deviations am I away from a typical person? So you take your distance from the mean, so like your number minus the mean, and we take it over how many standard deviations is that away. So divided by standard deviation. So our formula for that. Let's see. So like negative 1.8, I believe. So that means my score, my IQ score of an 82, I am negative 1.8 standard deviations below the average person. So like that's pretty low. I'm not very pleased with that test. So I could go to our formula chart online, or I'll pull one out here, and there is a table of values that say, let's just say like Maybe I'm gonna ask two questions. What percent of people did I beat, and what percent of people beat me? So, how many people are below me? What percent of people? So I look at my table of values. I go to negative 1.80. So negative 1.80. So the table, it tells me 0.0359. So,
Does that mean
pretty bad.
4%?
Yeah. Yeah, that means 3.59% of people are below me. So I did not do very good on this stuff. Or just not, whatever, not above many people. So another way to say this is, I guess reviewing, is percentile. Percentile is how many people are at or below your score. So like in this case, we could say, I don't know, we could round, I guess. And I could say that I'm in the 4th percentile, which is not good at all. Percentile, you want to be in like your SAT, you want to be really high, like the 90s and stuff, 80s, because you want to beat most of the people. But I'm only in the 4th percentile, so I'm really bad. So what percent of people beat me? So you just do, if I wanted to know the greater than, you just do 1, so 1 minus that, which is what? Giving myself way too much. Is that right? That looks right. 96.41% of people are below me. So like this percentage here is the percent above me. So it has to equal 1. That's the percent below. So like 96.4% of people beat me in that score. So using our table, using our z-score, understanding what these values mean, they just give us like the if our distribution's normal, here's these like probabilities of those in this like perfectly symmetric data. Okay. Are there any, maybe I'll do that. Are there any confusions on like these that y'all were like confused on if we did when we did the free response? Or might not know how to actually ask it.
Teachers, at this time, if you would please send students' last name K through P to the library for IDs. Again, please send students with the last name K through P to the library for IDs. Thank you.
Okay, so this idea of the normal distribution, we're going to use a lot in the second semester. So this whole calculation thing, understanding what these values are, we're going to get comfortable using that, and like we're going to interpret what these values mean a little more. Okay, let me talk about one more thing, and then we're going to get into probability. So alright, so how to collect our data, and these are just ways to take samples. Doing a simple random sample, stratified, or a cluster. So a simple random sample is like, I'm going to give every single person or element in my experiment the same chance of being selected. So you could do that like many different ways. You could, if it's 1 in 6 probability, you could roll a dice. If it's 50-50, you could flip a coin. You could put all your names in a hat and on a piece of paper and like shuffle it around and pick out if all the paper is the same width or whatever, there's nothing different about the paper. You could have like a lotto ball thing where they like spin the balls and then they shoot out a ball and pick a number. whatever it is, that's the basic idea of a simple random sample. You like number all, I guess you could say like the variables. So like I number all of you, whatever. I could give you the letters A through G or whatever. I give you some sort of thing. Then you use a random generator like a coin, a dice. Like those are not biased. If I use my own random choice, I might have bias. Like, oh, I chose a girl last time. I feel like I probably need to choose a boy because I chose a girl last time. Like, don't use yourself. So use a random number generator such as dice, calculator, coin, and then use sample. Alright, so that's pretty basic. Stratified and cluster are first, you split into groups. And so actually both of these, for the purposes of this, they both split into groups. But on stratified, I split into groups and then I choose an equal amount or like a representative amount from each group. So like I split you into like whatever. I don't have a lot of AP stat sections. So maybe like Miss Prejean splits her classes into her IB English sections and she samples 3 students from each of her IB sections, something like that. So stratified is split into groups and choose random number from each group. The difference in cluster is I split you into groups, or Miss Prejean, because she probably has 6 or 7 IB English classes, she splits you into those IB English classes, and then she chooses like 2 random classes and samples everybody in that class. So split into groups, choose a random group, sample entire group. So a slight difference, they're both split into groups. These are always mixed up with each other. And yeah, it's just thinking about, so like clusters are like you're grouped together until you like stay together. Once you're in your group, you're either randomly chosen and you get that whatever vaccine trial, or stratified is you're split into all these groups, maybe based on age, and they chose 3 teenagers, 3 20-year-olds, 3 30-year-olds, 3 40-year-olds. They got an equal from each group, equal number. So that's the difference. And those were some things on that free response that just felt like we needed a little reminder. Alright. Okay, so let's talk about probability again. I'm going to give you this little paper.
It's actually for
No, it's not. It's just me using the paper and not changing the header. Okay. Let's see. Yeah, y'all are gonna need some calculators too. So if you grab a calculator, if you don't have one, that would be good.
I'll go get you one.
So before we left, we were talking about some probabilities, and so like their distributions within them. So on this one, the probabilities a customer selects 1, 2, 3, or 4, 1, 2, 3, 4, or 5 items at a convenience store. And here's the probabilities of those. So 32% one item, 12%, 23%, 18%, 15% for 5 items. So we went through like graphing them. We talked about what was the mean, the expected average, what was the standard deviation, and we did some different things. So let's talk about the first one. Is this a legitimate probability distribution? So do y'all remember how we decided if it was legitimate?
If it adds to
Yeah, so if it's legitimate, all the probabilities add to 1. So do the probabilities add up to 1? I believe, like, yes, they do. At least they did for me before break. So hopefully they still do. Okay, B. If X represents the number of items bought, find the mean of the random variable X. Show how you got your answer. So what is the mean of X? So we wrote this 2 different ways. I didn't really get into the notation too much. One of them was like, oops, not like that. A way to say this is the expected number. So we did e to the parentheses, your variable, e to the x. So the expected number. You can also say it with the symbol that looks like it's like a M or a U. It looks like this to the x. Both those are the same thing. So on the calculator, we're going to do it on the calculator to get standard deviation, but by hand, I'll just write it out because it's not that crazy. You do like the probability of getting a 1, so 1 was 32%. So I'm going to give 1 a 32% chance. Plus, 2 items in a grocery store was 12%. Plus 3 items.
Teachers, pardon the interruption. Last group for IDs. You can send students the last name, alphabet Q through Z. Q through Z. Please send those students to the library to get their IDs made. Thank you.
Okay, so we talked about this one day. We did it by hand, but then we did it a lot just by calculator as well. But like you just take the percentage that item has, that number has of popping up, and you multiply by it. On the calculator, since we're going to do standard deviation, we can check it on there. So on the calculator, we're going to put this into a spreadsheet. We're going to make a list. So you make a new document, and you make yourself a list. The inspires are really particular, and so you always have to make sure to name it up here. So I'm going to name it like X, and then maybe I'll name it probability. You can name it whatever. You could say A, B, it doesn't matter. But you do have to name it. It like won't bring it up if you don't name it. All right, so like on the X's, it is 1, 2, 3, 4, and 5. Let me fix this color here. Menu. Why is it not working? Maybe you can see that a little better now. Okay, so 1, and then what are the others? 32%, so 0.32. Make sure to put the decimals. Alright, so you just make a list of whatever you named, whatever number value those one things have, the probabilities of those numbers popping up. And then you make a new page. So you go control doc, which is new page. So control doc, you add a calculator. So you just do number 1. And then I want some statistics on this. So I'm going to do menu, statistics. I'm going to do a calculation on the statistics. And this is for one variable. The variable is the number of items at the convenience store. So we only have one variable. You just leave it as one list. And then we're just going to focus on the X list and the frequency list. So the X list is, I labeled it X. You could have labeled it something different. And then the frequency list, I know on those calculators, it like pops up like stat max, stat this. You might have to scroll like all the way to the bottom to find what you labeled X and probability. But make sure you frequency list is whatever you put in as your probability list. And then leave those other two empty. You click OK. And it gives you your X bar. So this is the sum. So we're not using that. Like that. This is a different symbol than this. So those aren't the same. So don't do that. So we're actually using the X bar is the mean. That's another way to say mean. So 2.72, which is hopefully the way we did it by hand. Hopefully we got the same number. And then standard deviation is always this little O with a hat kind of thing. So standard deviation 1.44. Let's see, what did I say? I probably said 1.45, which I did. Okay. So 1.45. So when you get that, it was 2.72, hopefully by hand or calculator. And then the standard deviation of X is 1.45. So let's just talk about what that means, since we were lost in calculator world there for a little bit. So what this means is 2.72 convenience store items that we get. So this just means over like a lot of people coming into my convenience store, I expect about 2.7 items bought for like one person. So for every time I see a person come in my store, they're gonna buy like 2.7 items. So this is for like the long run. Obviously in the short term, I can't go in there and buy 2.7, but it's just an average in the long run. And then standard deviation means we typically vary like over a lot of people. A typical amount of people are 1.45 from that 2.72 items bought. So that means, what is that, like 1.3 to 4 point something. So about 1 to 4 items bought on a typical person walking into a convenience store. So that's just in context of that problem, like the interpretation, if it said to interpret. That just means over a lot of people we would expect this. Like for profit, like if I have about $3 items, I could say that 2 times $3. Like I can estimate some profit or some money coming in when I do that, which is actually what we're going to do down here at the bottom. So let's see. Alright, so I've got this value. So I need to pull this up for myself. Assume that the average price of an item bought is $2. Also assume that each customer donates $1 to special charity. So they're also going to add $1. So what this is for each item is $2, so we're multiplying 2, and then we're adding $1 in total. So every time a person comes in, for each item they bought, we're going to multiply $2 and add 1. So what's the mean and what's the standard deviation now? So let's see. So our mean was 2.72 items bought. And so we're expecting that they pay me $2 for each of those items. And then on top of that, they're going to add $1 given to me at the end. So the average person is going to pay 2.72 times 2 plus 1. Yeah, it's about $6.44. That'd be like the average amount of money they're spending. Okay, the standard deviation is 1.45, and I expect them to give me $2 for that. But with standard deviation, so standard deviation is never affected by plussing and minusing. So when you plus and minus to like a distribution, so let's say like this, I don't know, let's say this is my distribution, and let's say I add $1 to everything, so like now my thing becomes like this. That was pretty good. The mean, so let's just say this is our mean, so the mean gets shifted, but the standard deviation, like let's say this is my standard deviation, it doesn't change. It just like, it still becomes the same width. The width of it doesn't change just by adding. So when I come back to this, the addition or subtraction doesn't change. So no change in standard deviation for plus or minus. So when you add or subtract, the spread doesn't get affected. So all I have to do is just multiply by 2. So we talked about this one day too. So just the importance of like, what's the effect of multiplying, what's the effect of adding. And standard deviation is always what we have to worry about. It always has something different. So let's see, that was like $2.90, 2.9 is the standard deviation. So it's not $3.90 because that plus doesn't change the spread. The spread didn't get affected. But like, so if I went back here, it's like the spread does get affected when you multiply. So like, if I had this distribution from like 2 to 6, if I multiply, so let's say I multiplied by 2, now this is at 4 to 12. So now, this is now my graph when I multiply by 2. So multiplying does change the spread. The spread gets bigger by multiplying. But if you plus and minus, it doesn't change. It's kind of a weird concept. It like makes sense, but then when you're doing the problems, you easily forget about it. So, alright, so trying that out. So, multiplying, adding to the means and standard deviations. Alright. Cool. Okay. Other thing, number 3. So we're gonna skip number 2 and go to number 3. So the other thing we talked about was combining these two means and standard deviations. We did a problem that was like talking about these like Jeep tours, where like this brother and sister were doing these tours, and like this person has this many people, whatever. So on this one, 2005 baseball season, the Phillies runs per game is X, the Yankees runs per game is Y, so they have about 3.7 runs per game, standard deviation 1.1 from that, so kind of typical value plus or minus 1.1. The Yankees were 4.9, 1.6. Okay, so what is the mean of those added together? What's the mean of those subtracted? What's the standard deviation? So what is the average number of the Phillies and the Yankees combined? Averages are normally pretty simple. You just take what your average was and you add them together. So like we were expecting the Phillies to have 3.7 and the Yankees 4.9. So like we expect them together, if they played each other, to score, what is that, 8.6 runs? That's right. So like if the Yankees and the Phillies played each other, I would expect about 8.6 runs scored that game. That would be like an average amount if they played a lot in that season. That in total there would be 8.6 runs scored. Okay, like on this one, find the average of Yankees minus Phillies. So this is asking like how many more runs do the Yankees score, basically, if they didn't put it into context. And so that would be like the Yankees score 4.9 typically. The Phillies score about 3.7. So the Yankees would typically beat the Phillies by about a run, is what that means. So obviously there's every game is different, and maybe this is over the long run, and sports are hard because maybe there's a pitcher or someone gets hurt or there's pressure situations, whatever, but this is like combine the difference. Okay, things always get weird with standard deviations though. And so what would be the standard deviation of this game? So this is like the Yankees win by a run when they typically play. But what is our variation? Like what's the typical amount of variation? So let's see. So you don't, with standard deviations, we never just, standard deviation is calculated, which y'all don't have to do it by hand, so like don't worry about this. It's calculated by like the square root of the sum of like a number minus a mean squared over a number. So like it's a square root number. You can't add square roots together. So the way we combine these things together is I do the standard deviation of Yankees squared and the standard deviation of the Phillies squared. And then the other weird thing about standard deviations is that they'll never get smaller. Your unpredictability always gets bigger when you combine things. So I'm never subtracting, I'm always adding standard deviations. So even though it says subtract there, I'm always adding. So you can think about it as it's only more unpredictable now. So it's only going to increase my unpredictability. Standard deviation is like your wiggle room. Like, I expect them to score this many runs, but plus or minus 1 or 2 runs from there. So that only adds together when you do it. Okay, and then you actually have to do one more thing. So when I square them, I square them, I add them together. I then have to undo the square again with another square root. So standard deviations are a ton of fun. They have all the complicatedness. So it would be the standard deviation, or the square root of I guess it'd be y. So 1.6 squared plus 1.1 squared. Okay, so a long way to finally get to an answer. So you do standard deviation squared, then square the other one, then combine them, then square root that, and it should be, at least before, I got like 1.94. And so what this means is, like, if we look at these two together, I expect the Yankees to have an average of like 1.2 more runs, but like plus or minus 1.94 is a typical. So obviously, like, there's some wiggle room for like the Phillies to win a game, if I was to put that into context. If I was to draw that out, like the Yankees, what was it, 1.2? So they typically score about 1.2 more, but like, here's them tying. So here's like the Phillies winning. Here's the Yankees. And so the standard deviation was like minus 1.9 plus 1.9. That's like a typical value. And so there's more outside of one standard deviation. And so obviously, like, the Phillies have some sort of chance of winning. And so you could calculate it. You could do a normal distribution if they're normal. You could do a bunch of different things. But that's kind of the thing. So the spreads, they only get more unpredictable. So I would never lessen the unpredictability. When I'm combining things, they only get bigger in unpredictability. And then this whole squared thing. It's a little weird, a little strange. The means are really easy. Like, you just add or subtract them. Standard deviations, normally more complicated. Alright. So what I want you to do is, I've got another paper that says quiz on it. Please don't be alarmed. It's just a worksheet that we're going to do, and you've got plenty of time to do it before class. If you want, you can turn it, there's a place on Schoology for you to turn it in, or you could just turn it into the box up front if you'd rather just do that. So turn this in on Schoology or up here where it's the second period. And we'll move on to some more probability tomorrow. But doing the assignment, it's like a couple problems, just like what we did. Try them out.